Good afternoon, class. We are looking at Chapter 3, Polynomial and Rational Functions. Here's Section 3.6, Inverse and Radical Functions. So in this section, Inverse and Radical Functions, we are covering the following objectives. Find the inverse of an invertible function. Restrict the domain to find the inverse of a function. Here's a summary of polynomial functions. Polynomial functions are in the form of f of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0, which is the constant. A sub n x to the power of n is the leading term. A sub n, which is the leading coefficient, cannot be 0. N is a whole number, meaning 0, 1, 2 to infinity. The domain for all polynomials is all real numbers from negative to positive infinity. Two simple examples. A polynomial of degree 1, a linear function p of x equals mx plus b, quadratic function p of x equals ax squared plus bx plus c, which has its vertex at minus b over 2a, and you plug in to find the y-coordinate. Degree of the polynomial f of x is n, graph is smooth and continuous, maximum number of turning points is n minus 1. At a 0 of even multiplicity, the graph of f of x touches the x-axis. At a 0 of odd multiplicity, the graph of f of x crosses the x-axis. Between zeros, the graph of f of x is either above or below the x-axis. And the end behavior, that means for large absolute values of x, as x approaches negative or positive infinity, the graph of f of x behaves like the graph of its leading term, y equals a sub n, x to the power of n. Zeros of polynomials. N of x divided by d of x is q of x plus r of x over d of x, where n is the dividend, d is the divisor, q is the quotient, r is the remainder, or you can do the cross product. N of x is q of x times d of x plus r of x. The remainder theorem indicates if you're dividing f of x by x minus c, r is simply f of c. Plug it in and evaluate f of x at c. And if that remainder is 0, it becomes, remainder theorem becomes a factor theorem. The IVT, the intermediate value theorem, if f of x is a polynomial function or any continuous function. And if for real numbers a and b, the values f of a and f of b are opposite in sign, then there exists at least one real 0 between a and b. Numbers of zero theorem. A function defined by a polynomial of degree n has at most n distinct, unique, complex zeros. The rational zero theorem indicates that if f of x is given as before, a sub n x to the power of n all the way to a sub 0, then p over q, the possible rational zeros, would be factors of a sub 0, the constant, over factors of a sub n, the leading coefficient. Fundamental theorem of algebra indicates if p of x is a polynomial of degree 1 or more, then there is some number k such that p of k equal to 0. Then p of x equals x minus k times q of x. And when you expand that, where q of x can also be factor, resulting in p of x equals a times x minus k sub 1 all the way to x minus k sub n. Conjugate zero theorem indicates if p of x defines a polynomial function having only real coefficients, and if r equals a plus bi is a 0 of p of x, then its conjugate r bar a minus bi is also a 0 of p of x. Therefore, odd degree polynomials have at least one real 0, since complex conjugate zeros happen in pairs. That's the reason. rational functions. A function f is a rational function if f of x is in the form of n of x over d of x. As always, d of x, the denominator can't be zero, where n and d are both polynomials. The domain of f consists of all real numbers except the zeros of the denominator of f of x, which is d of x. Rational function in lowest term, f of x equals n of x over d of x. Then VA, short for vertical asymptote, you set the denominator equal to zero. It's important to put it in lowest term first. Finding the horizontal and oblique asymptote of a rational function. If f of x is n of x over d of x, such that the numerator is a sub n x to the power of n all the way to a sub 0, and the bottom is b sub m x to the power of m all the way to b sub 0, which means the degree of the numerator is n, the degree of the denominator is m. If n is less than m, horizontal asymptote has the equation y equals 0. If n is equal to m, then the leading coefficients a sub n over b sub m take over, and horizontal asymptote y will be equal to that. If n is precisely m plus 1, we divide the top by the bottom. It results in a linear function mx plus b and remainder over d of x. Then oblique asymptote, also known as slant asymptote, will be y equals mx plus b, this quotient. So oblique or slant asymptote. In 3.6, inverses and radical functions. Function. For each x in the domain of f, there is exactly one image f of x in the range. However, an element in the range can result from more than one x in the domain. So that's the definition of a function. What does it mean? The x coordinate cannot repeat. Determine whether a function is one-to-one. Now, a function is one-to-one if each element in the range corresponds to exactly one element in the domain. So a function is one-to-one if the y coordinates cannot repeat either. A function f is one-to-one if for any two numbers a and b in its domain, f of a equals f of b results in a being equal to b, and when a is not equal to b, results in f of a not being equal to f of b. In other words, x1 is not equal to x2. That means f of x sub 1 cannot be equal to f of x sub 2. Determine whether a function is one-to-one. Well, let's look at the first one. The x coordinates, the y coordinates, each one are unique. So we have a function, we also have a one-to-one function. In this case, the x coordinate repeats with y sub 1, and again y sub 1, x sub 1, y sub 1, x sub 2, y sub 1. So no. Okay, so you can write this pair, and you can write this pair, x sub 1 comma y sub 1. Let's write it. So this means this, and this means this pair. X sub 1, x sub 2, y sub 1. So the y coordinate is being repeated, and that's not a one-to-one function. The last one is not a function because let's write this also, x sub 1, y sub 1. This means x sub 1, y sub 2. X is being repeated in this case. In this case, y is being repeated. So the answer is no for this one. The answer is no because 55. So let's write those. This means 55, 38. This means 61, 38. The y coordinate is being repeated, and the answer is no. This one, the x coordinates are not repeating, it's a function. The y coordinates are not repeating either. So yes, it's a one-to-one function. Quickly, x coordinates, they are all different. That makes it a function. Y coordinates, 6, 3, 2, 5, 8, they are different. That makes it a one-to-one function. Continuing with one-to-one function, horizontal line test HLT. If a horizontal line can be drawn so that it intersects the graph of a function at more than one point, the graph is not a one-to-one function. No horizontal line can intersect the graph more than once. This example, that means the y coordinate is the same for this point and this point. If you look at this one, is this a function? Yes, it passes the vertical line test. Is this a one-to-one function? No, it fails a horizontal line test. However, if we cut it from the vertex into two halves, each half is a one-to-one function. Monotonic functions are one-to-one functions. Monotonic function is either increasing or decreasing on an interval. If keeps on increasing and nothing else, or keeps on decreasing and nothing else, it's called a monotonic function, and they're one-to-one. So one-to-one function, x of 1 can't be equal to x of 2, results in f of x of 1 can't be equal to f of x of 2. On the other hand, not one-to-one. If f of x of 1 equals f of x of 2, if f of x of 1 is equal to f of x of 2, but x of 1 is not equal to x of 2. For each function, use the graph to determine whether the function is one-to-one, and we're going to use the HLT, horizontal line test. This is a graph that you know how to do it. It's a parabola. Everybody is familiar with the graph. Clearly, it fails a horizontal line test. If you draw one example, this one, y equals 1. So x squared equals 1, x is plus minus 1, it has two pairs and it fails the HLT, therefore it is not a one-to-one function. Y equals x cubed looks like that. There is no way to draw any horizontal line that crosses the graph more than once, and by the way, this is monotonic, it's completely increasing all the time. So that makes it a one-to-one function. Inverse of a function defined by a map or a set of ordered pairs. If f of x is a one-to-one function with ordered pairs of the form x comma y, the inverse function f inverse of x is a one-to-one function with ordered pairs of y comma x. So here's domain of f, here's range of f, and f maps f to its range, and coming back, this would be the domain of f. Range of f coming back, this would be domain of f inverse. Range of f inverse is this one. And in short, x and y interchange. So suppose that f is a one-to-one function. Then corresponding to each x in the domain of f, there's exactly one y in the range, because f is a function. And corresponding to each y in the range of f, there is exactly one x in the domain, because f is one-to-one. So we really should pay attention to the reason as to why this is the case. the correspondence from the range of f back to the domain of f is called the inverse function of f. The symbol f inverse is used to denote the inverse function of f. So, f inverse of x represents pairs b comma a such that, I've gone over that, this means such that a comma b is an element of f of x. So in short, interchange x and y. That is the definition of f inverse. F inverse contains all the pairs b comma a such that a comma b is an element of f of x. So let me write this again just to make sure this line segment reads such that, and this thing reads an element of, this is from the set theory, domain of f is range of f inverse, range of f is domain of f inverse. So very straightforward. We had seen this stuff and hopefully it's coming back to us. Given the function f of x, 1 comma 4, 2 comma 0, 3 comma 7, minus 2 comma 1, negative 1 comma negative 5, find the inverse function. Well, all you have to do, interchange x and y, everybody. That's all you have to do. Therefore, 1, 4 becomes 4, 1, 0, 2, 7, 3, 1, negative 2, negative 5, negative 1. And if you graph them carefully, you can see, of course, as expected, they are symmetric with respect to the line y equals x. Points for the two functions are symmetric with respect to the line y equals x because you're interchanging x and y. So 3, 7 and 7, 3, by the nature of x, y, and y, x now, they are symmetric with respect to the line y equals x when you change x and y, and the rest of them 0, 2, 2, 0, 1, 4, 4, 1, and so forth. Verifying inverse functions. G of x is x squared, G inverse of x is cube root of x. To verify that, we follow the following theorem. For any one-to-one function f of x and its inverse f inverse of x, f o f inverse of x is x, f inverse of f inverse o f of x is x. In this case, x is in the domain of f inverse, this one. In this case, x is in the domain of f. So if we want to look at g of a g inverse, that means replace this x with cube root of x. That's the meaning of it. Replace the x with cube root of x. And of course, the answer is x. So that's a proof and you're done. However, for practice, let's look at g inverse of g of x. When we do that, that means g inverse is cube root of x. Replace the x with x cubed. And of course, they cancel each other. They give us x. Let's do the same thing here. F of x is 2x plus 3. F inverse of x is 1/2 x minus 3. So we are going to write f o f inverse or f of f inverse of x. That means replace the x with f inverse. As we do that, 2 and 1/2 cancel each other. We end up with x minus 3 plus 3, and the answer is x. Let's look at f inverse of, which means replace this x with the f function, 2x plus 3. And as you can see, these two cancel each other, and the product of these two is x, and that's a proof that the two functions are inverse of each other. And again, you don't have to do both ways, class. I can't emphasize this enough, but it's a good practice to look at them both, okay? We continue verifying inverse functions where f of x is 3 over x plus 5, f inverse is 3 over x minus 5, and then for what values of x is f inverse of f of x equals x, for what values of x is f of f inverse of x equals x. We're going to discuss that in a moment. Remember the domain of f, if you look at f, it's all real numbers except what makes the denominator 0. So if you set x plus 5 equal to 0, gives you x equals minus 5. So that's why domain is all real numbers except minus 5 for f of x. For f inverse, x can't be 0. So all real numbers except 0. So we are going to look at f of f inverse of f of x first. So first, I want you to know as far as this part is concerned, because it's asking for f inverse of f of x equals x first, and for what value you have to be careful. The value that we got to be careful is the x coming from f of x. If you look at f of x, x can't be minus 5. So we already know the answer to this part comes from f of x. So x can't be negative 5. Let's work on it, meaning we pick this function and we replace the x with this function. So we are dealing with a complex fraction, which means, let's say this is 3 over 1. So multiply these two, multiply these two. These two cancel each other. We get x plus 5 minus 5, which is x. And that is if x is not equal to negative 5, it comes from here. Okay. What about f of f inverse of x? So we go to this function and replace the x with 3 over x plus 5. So 3 over x minus 5. This x is replaced by this. My apologies. F of f inverse of x. This x is replaced by that. Okay. And so 3 over x plus 5. These two cancel each other. We have 3 over x, and this is a complex fraction. Multiply these two. We get 3x. Multiply these two, we get 3. They cancel each other, the 3 and 3, and they give us x. In this case, x can't be 0, and it comes from here. Graphing the inverse functions. Theorem: graph of the inverse functions f of x and f inverse of x are symmetric with respect to the line y equals x. So all you have to do to see the reason, if this is the line y equals x, point A comma B and B comma A, if you connect them, this distance is equal to this distance when you interchange x, the x coordinate and y coordinate. Okay, they have the same distance simply because you're interchanging it. So it's symmetric with respect to the line y equals x. Again, you pick this point, you drop a perpendicular, and you go the same distance. It will take you to B comma A. So a graph looking like that, you can use this concept of asymmetry with respect to y equals x, and it looks like that. By the way, if the two functions f of x and f inverse ever intersect, they may not intersect, but if they do, that means the x coordinate and the y coordinate are interchanging. The x coordinate of one is equal to the y coordinate of the other. Therefore, it can only happen that they intersect with the line y equals x. So, what do we do here? Let's pick up the points that are given and come up with a point on the graph of its inverse. So, for example, this one will result in this one. So -2 comma -1 gives us -1 comma -2. So 1 to the left, 2 down. And of course, symmetric with respect to this line. We pick the next one, -1, 0 results in 0, -1. So 0, -1. The last one is 2, 1, results in 1, 2. So 1 to the right, 2 up. Okay. And you just connect those, and it will look like this. So here's the given piece, and here's the new piece that we come up with. Both of them are functions, and they are inverse functions. All right. Finding inverse functions. Only one-to-one functions have inverse functions. The domain of f is the range of f inverse. The range of f is the domain of f inverse. The graphs of f and f inverse are symmetric about the line y equals x. When graphed on the same axis, f of a equals b, that means f inverse of b equals a. If AB is one point on f of x, BA is a point on the inverse function. This is the definition of inverse function. To find the inverse function of a one-to-one function, and by the way, this -1 in f inverse is not an exponent. You remember that it's read f inverse. First, replace f of x with y, because it makes it easier to work with. Then interchange x and y. right? At step 2, we do have the inverse. However, we don't leave it like that. We always solve for y. When we're done, we replace this resulting y with f inverse. That is the inverse function. And of course, it's a good practice to check your work. We want to find the inverse of f of x, where f of x is given as 2x plus 3, and we want to graph the two functions. So step 1, replace f of x with y, again, because it makes it easier to work with. Step 2, interchange x and y, so call this x, call this y, that is x equals 2y plus 3. And we are going to solve for y. We're going to move the 3 to the other side, subtract it from x. And we're going to divide both sides by 2. So y is 1/2 of x minus 3, or x minus 3 over 2. Give it the name f inverse, and you're done. Now let's check f of f inverse of x. That means here's the f function. Replace this x with this. So replace this x with this. 1/2 and 2 cancel each other. X minus 3 plus 3 is x. Let's look at f inverse f of x. In this case, over here, this x is replaced by 2x plus 3. As you can see, positive 3, negative 3 cancel each other. The product 1/2 and 2x is x. So both of them verify the same thing. The two lines we want to graph, this one obviously has 0, 3 as the y-intercept. If you set f of x or y equal to 0, x becomes negative 3/2. For the inverse, you don't have to do any calculation, interchange. This becomes 3, 0, and this becomes 0, negative 3/2. I hope you notice if you plug in 3, you do get 0. And if you plug in 0, you get 1/2 times minus 3, which is negative 3/2. So all you have to do, plot those two pairs and those two pairs, put them together, and you get the two graphs. This is f of x. The blue one is f of x to x plus 3. The red one is f inverse 1/2 of x minus 3. And of course, symmetric with respect to the line y equals x. And because they do intersect, they have to intersect somewhere on the line y equals x. Find the inverse of f of x equals x squared if x is greater than or equal to 0. Please pay attention to the fact that you are dealing with a function which is not a one-to-one function. When x is larger than or equal to 0, you're restricting it so it becomes a one-to-one function. And graph f and f inverse. So replace f of x with y because it makes it easier. Y equals x squared. Interchange x and y. That means now this is x, this is y squared. And now we're going to say y is larger than or equal to 0 because right here we have the inverse. Domain x is larger than or equal to 0 for f of x. Range y is greater than or equal to 0 for its inverse. Domain of f of x is range of its inverse. So y, if you solve, is plus minus square root of x, but it's positive. Therefore, only y equals square root of x. So it's important. This results in this. If this wasn't there, class, y would be plus minus square root of x. But with the combination of this, we have only one solution, y equals square root of x. And that's important to understand. Now we give it a name. F inverse. Let me erase my word. Now let's prove that it's correct by looking at their composite function. So we're going to look at f of f inverse. And again, reminding everybody that when f inverse of x is the square root of x, domain of f is range of f inverse. Okay. So that's why we have this one, or 0 to infinity. Domain of f inverse is range of f, and it happened to be 0 to infinity also. Because you know the domain for this one. You should know the domain for this one. Oh, that's x is larger than or equal to 0. That's why we get to this result. Okay. All right. F of f inverse means plug in this one into this. And of course, the answer is x. F inverse f of x, that means plug this one into this. Square root of x squared. It's important to know it's the absolute value of x. It's not x. However, the reason it changes to x because we know x is greater than or equal to 0. It's important. X comes from here, and we said x. So this is the reason, everybody. This is the reason you can do that. Otherwise, square root of x squared is absolute value of x, which could be positive or negative x in essence. That's the meaning of it. But we know x is larger than or equal to 0. The answer is x. And you know how to graph this y equals x squared. That's a parabola. And we have only the right half because x is larger than or equal to 0. And we know this is the graph of y equals square root of x, or f inverse. So this is a parabola. We don't have the left half. It's just the right half, okay? And this is the graph of square root of x. By the way, if I graph it just for the sake of argument, this portion class, okay, is not there because of this one, okay? However, if you look at this portion of it, okay, this one, if you flip it over, then this and this would be inverse functions, okay? So this part goes with this part. This half, if you choose x less than or equal to 0, is this half. Then it goes with this one minus square root of x. You can try that if you like. Find the inverse of f of x, where f of x is 2x plus 1 over x minus 1. Obviously, x can't be 1, right? Set the denominator equal to 0 and excluded, and graph f and f inverse. So first we replace f of x with y to make life easier. The second step is to interchange x and y. So this becomes x, this becomes y. To solve for y, we do the cross product. X times y minus 1, 1 times 2y plus 1. We want to solve for y. So we bring everything involving y together. This is xy minus x. So this moves this way, and this moves this way. We end up with xy minus 2y is x plus 1. Now, on the left side, if I factor the y out, I get x minus 2. If I divide both sides by x minus 2, because I'm solving for y, I get to the answer. But I'm going to change the name to f inverse. And of course, x can't be 0. X can't be 2, my apologies. Look, I mean, the denominator can't be 0. Therefore, x can't be 2. Now we're going to look at their composite function. So I'm going to look at f of f inverse. Remember, f of f inverse equals f inverse of x equals x. Sometimes you just write this, sometimes you don't. I didn't write it here. I wrote it here on purpose. Either way is fine. This is a shorthand notation. It's just good. So if we want to go with f of f inverse, that means f of f inverse of x. That means in this function, replace each x by this fraction x plus 1 over x minus 2. That's the meaning of it. Now, this is a complex fraction. By the way, I'm going to just do this one. I'm not going to do that one. I highly recommend you do that for practice. So, complex fraction, an easy way out, you multiply the top and the bottom by denominator, which is x minus 2, which is the LCD. So when I multiply the top by x minus 2, please pay attention, see what happens. I multiply this part by it. So the denominator goes away. I get 2 times x plus 1. Then I multiply this one by it plus 1 times x minus 2. I multiply this one by this one. It cancels out the denominator and just gives me the numerator x plus 1 minus 1 times x minus 2. I hope everybody can follow this basic elementary algebra. So we have 2x plus 2 plus x minus 2 up here. Over here we have x plus 1 minus x plus 2. So these two cancel each other, and the numerator becomes 3x. These two cancel each other. The denominator becomes 3x over 3 is x, and it checks. So we proved we've come up with the correct answer. Again, I highly recommend this. You do f inverse OF for practice. Now, so here's the function f of x. Here's the inverse f of x. Of course, x can't be 1. F inverse x can't be 2. And we are going to look at the graphs. I'm not going to go over the details of the graph, assuming you can graph and by now remember. You find the asymptote, this one, x equals 1. The vertical asymptote, the horizontal asymptote, y equals 2. You find the intercepts, and you do the same thing here, you graph. So if you look at this graph, it has the horizontal asymptote y equals 2, vertical asymptote x equals 1. And if you look at these 2 points, the intercepts, when you set y equal to 0, 2x, that means a fraction is 0 when the top is 0, x becomes negative 1/2. That's why you have negative 1/2, 0. This one is negative 1/2, 0. If you set x equal to 0, you get -1, and this one is 0, -1. Let's look at the graph of its inverse. Again, you can graph it, but I want you to compare asymptotes and intercepts. Here's the vertical asymptote x equals 1. Here's the horizontal asymptote y equals 1. Here's the horizontal asymptote y equals 2. Here's the vertical asymptote x equals 2. Do you see that? X equals 2 and 1/1. So they make perfect sense. So we have 0 minus 1. We're going to have -1, 0. We have negative 1/2, 0. We're going to have 0, negative 1/2. Look at those 2 pairs. Okay. So that gives you an idea that it works perfect. Again, I have no doubt that you guys remember the previous section and you can graph this easily. Find the inverse of a function. Find the inverse of f of x equals x squared minus 2. Again, if x is larger than or equal to 0, remember, y equals x squared or y equals x squared minus 2 for that matter is not a one-to-one function. The restriction on the domain makes it so. Remember, what is this graph? This is a parabola that has been shifted down by 2 units. So when we do that, we are looking at the right half. Okay, just quickly, this is the graph, everybody. Y equals x squared has been shifted down by 2 units. And this means only this half, not this part. Okay, that's the meaning of it, just to give you an idea. So I'm going to clean out the page so we can see what happens next. We're going to replace f of x with y to make life easier. So we get y equals x squared minus 2. We are going to interchange x and y. So this becomes x, this becomes y squared minus 2. And right here, it's important to know we have the inverse here. However, we solve for y. X is greater than or equal to 0 for f of x. That means y is greater than or equal to 0 for its inverse. Okay, remember, domain of f becomes range of f inverse and vice versa. You want to solve for y. We are going to move this -2. And we're going to take a root. And y is normally going to solve for y. Is plus minus the square root of x plus 2. However, so if you're solving this, it gives you y equals plus minus square root of x plus 2. However, this indicates only the positive one is acceptable. Okay, so again, want to make sure we understand what happens here. We are given x is larger than or equal to 0. That means 0 to infinity, by the way. Okay, that means you're dealing with bracket 0 comma infinity. That's the meaning of it, right? As far as the domain is concerned. And so because this is the case for x, then this should be the case for y for its inverse. And this is the inverse, everybody. The moment you interchange x and y, you find the inverse. However, we solve for y, we give it a name f inverse, and therefore f inverse of x is square root of x plus 2. And x must be greater than or equal to negative 2. Why is that? Because you are dealing with the square root. X plus 2 must be greater than or equal to 0, which gives you this one. Okay. Which means this. So I want to make sure we understand that. If the domain for f of x is from 0 to infinity, the range for the inverse is 0 to infinity. If the domain for f inverse is minus 2 to infinity, the range for that one is minus 2 to infinity. And even the graph that I showed you indicates that. Now, let's verify the work by looking at the composite function. For example, f of f inverse of x, meaning into this function goes this square root of x plus 2. Of course, the two cancel each other, and this comes out as x plus 2, and with negative 2 we get x, and that's a verification that we came up with the correct answer. And so what I just mentioned before, I'm going to write it here. When f of x is x squared minus 2 and f inverse of x squared of x plus 2, domain of f is range of f inverse 0 to infinity, and domain of f inverse is range of f negative 2 to infinity. And so if you graph, remember, this was a parabola, and we just got rid of this left half, and we have the right half. So this is f of x, which is x squared minus 2. This is f inverse, which is square root of x plus 2, the red one, okay? And again, you can see that they're symmetric with respect to the line y equals x. If they ever intersect, and they do, has to happen on the line y equals x. And notice minus 2, 0, over here we have 0, minus 2, and the rest of the stuff. So everything that we discussed with respect to inverse functions, it works perfect here.